Unlike internal combustion engine (IC) vehicles, EVs rely on electric motors powered by rechargeable battery packs, offering cleaner, quieter, and more efficient performance. In this video, we delve into the mechanics of how electric car motors work, explores the latest innovations in electric motor design, and highlights cutting-edge developments in EV battery technology, providing a comprehensive look at the heart of electric mobility. How electric car motors work. The basics of electric motors. At the core of every EV is an electric traction motor, which converts electrical energy into mechanical energy to drive the vehicle's wheels. Unlike ICEs with hundreds of moving parts, electric motors are remarkably simple, typically featuring just one moving component, the rotor. The motor consists of two primary parts, the stator, the stationary part, and the rotor, the rotating part. These components work together through electromagnetic principles to generate motion. When the driver presses the accelerator, the battery sends electrical energy to the stator, a cylindrical housing containing coils of copper wire or electromagnets. These coils are energized to create a rotating magnetic field, RMF. The rotor, positioned inside the stator, is either equipped with permanent magnets or conductive bars in induction motors that interact with the RMF. This interaction causes the rotor to spin, producing mechanical torque that is transferred to the vehicle's wheels via a simple gearbox or direct drive system. Electric motors in EVs primarily use alternating current, AC, because AC motors, such as three-phase induction or synchronous motors, provide consistent torque and efficiency under varying conditions. However, EV batteries store and supply direct current, DC. To bridge this gap, an inverter converts DC from the battery into AC for the motor, while also controlling the motor's speed and torque by adjusting the frequency and amplitude of the AC power. Types of electric motors. There are three main types of electric motors used in EVs, each with distinct characteristics. 1. AC induction motors. Pioneered by Nikola Tesla, these asynchronous motors feature a stator that generates an RMF, inducing a current in the rotor's conductive bars, often copper or aluminum. The rotor lags slightly behind the RMF, creating torque. Induction motors are robust, cost-effective, and require minimal maintenance, making them popular in vehicles like the Tesla Model S. 2. Permanent magnet synchronous motors, PMSMs. These synchronous motors use permanent magnets in the rotor, which align with the stator's RMF to rotate in lockstep. PMSMs are highly efficient and compact, offering excellent power density. They are used in vehicles like the Nissan Leaf and Tesla Model 3. However, they rely on rare earth magnets, for example, neodymium, which can be costly and environmentally challenging to source. 3. Electrically excited synchronous motors, EESMs. A newer alternative, EESMs generate the rotor's magnetic field using an external electrical current instead of permanent magnets. This eliminates the need for rare earth materials, reducing costs and environmental impact. BMW's i4 and iX use EESMs, showcasing their potential for high efficiency and scalability. Regenerative braking. A standout feature of EV motors is regenerative braking. When the driver lifts off the accelerator or applies the brakes, the motor reverses its function, acting as a generator. The rotor's motion induces an electric current in the stator, converting kinetic energy back into electrical energy, which is fed back to the battery. This process improves efficiency, extending the vehicle's range by up to 20% in urban driving conditions. Key components supporting the motor. Several components ensure the motor operates efficiently. Power electronics. Controller manages the flow of electrical energy, controlling motor speed and torque. DC-DC converter converts high-voltage DC from the traction battery to lower-voltage DC for auxiliary systems like lights and infotainment. Onboard charger converts AC from charging stations to DC for battery charging, monitoring voltage, current, and temperature. Thermal management system maintains optimal temperatures for the motor, battery, and electronics, preventing overheating and ensuring longevity. Latest innovations in electric motors. Electric motor technology is evolving rapidly, driven by the need for greater efficiency, reduced costs, and sustainability. Below are some of the latest advancements as of 2025. 1. Rare earth-free motors. The reliance on rare earth magnets in PMSMs has spurred research into alternatives due to supply chain constraints and environmental concerns. Electrically excited synchronous motors, EESMs, are gaining traction, as seen in BMW's i4 and X. These motors use copper windings to generate the rotor's magnetic field, eliminating rare earth materials while maintaining high efficiency. Companies like Renault are also exploring wound rotor synchronous motors, which offer similar benefits with improved manufacturability. 2. Axial flux motors. Axial flux motors are emerging as a game-changer for EVs. Unlike traditional radial flux motors, where magnetic fields flow radially between the stator and rotor, axial flux motors direct magnetic fields along the motor's axis, resulting in a flatter, more compact design. These motors offer higher power density and efficiency, making them ideal for high-performance EVs. Companies like Mercedes-Benz and startup YASA, acquired by Mercedes in 2021, are integrating axial flux motors into luxury models like the AMG.EA platform, achieving up to 20% better power-to-weight ratios. 3. Hairpin winding technology. Hairpin winding replaces traditional round copper wires with rectangular, hairpin-shaped copper bars in the stator. This design increases the copper fill factor, improving torque density and reducing energy losses. The result is smaller, lighter motors with enhanced efficiency. Automakers like Volkswagen and Tesla are adopting hairpin windings in their latest EV powertrains, such as the ID, Series and Model Y, respectively. 4. Integrated powertrains. Modern EVs are moving toward integrated powertrains, combining the motor, inverter, and gearbox into a single unit. This reduces weight, size, and manufacturing complexity while improving efficiency. For example, Tesla's Plaid powertrain integrates these components, delivering instant torque and a compact footprint. Renault's Zoe powertrain also showcases this trend, with innovations like optimized gear motors for smoother performance. 5. Advanced materials and cooling. New materials such as silicon carbide, SOIC, and inverters reduce energy losses and improve thermal efficiency, allowing motors to operate at higher voltages and temperatures. Additionally, advanced cooling systems, like direct oil cooling, enhance motor durability by dissipating heat more effectively. These innovations are critical for high-performance EVs, such as the Rimac C2, which pushes motor performance to extreme levels. 6. Dual motor and multi-motor configurations. High-performance EVs increasingly use dual motor or tri-motor setups to deliver all-wheel drive and precise torque vectoring. The Tesla Model S Plaid, with its tri-motor configuration, achieves unprecedented acceleration, 0 to 60 miles per hour in under 2 seconds, by independently controlling torque to each wheel. This trend is expanding to mainstream models, with vehicles like the Jaguar Y-Pace using dual motors for enhanced traction and handling. Latest innovations in electric car batteries. Batteries are the backbone of EVs, determining range, charging speed, and cost. Recent advancements are pushing the boundaries of energy density, sustainability, and performance. 1. Solid-state batteries. Solid-state batteries replace the liquid electrolyte in traditional lithium-ion batteries with a solid electrolyte, offering higher energy density, up to 50% more than current lithium-ion packs, faster charging, and improved safety due to reduced flammability. Toyota is leading the charge, aiming to commercialize solid-state batteries by 2027, with prototypes already achieving ranges exceeding 600 miles. Startups like QuantumScape are also making strides, with Volkswagen-backed trials showing 500,000-mile lifespans. 2. Silicon anodes. Traditional lithium-ion batteries use graphite anodes, but silicon anodes can store up to 10 times more lithium, boosting energy density by 20 to 40%. However, silicon expands significantly during charging, risking degradation. Innovations like silicon carbon composites and nanostructured silicon mitigate this issue, stabilizing performance. Companies like Sella Nanotechnologies are integrating silicon anodes into EV batteries, with Mercedes-Benz planning to adopt them for the EQG by 2026. 3. Lithium iron phosphate (LFP) batteries. LFP batteries are gaining popularity due to their lower cost, longer lifespan, up to 2,000 cycles, and safety advantages over nickel-based chemistries. They avoid cobalt and nickel, reducing ethical and environmental concerns. Tesla's Model 3 and BYD's Blade battery use LFP, offering ranges up to 300 miles while maintaining affordability. Advances in LFP energy density are closing the gap with premium chemistries, making them a staple in mass-market EVs. 4. Ultra-fast charging. New battery designs and chemistries are enabling ultra-fast charging, reducing charge times to under 15 minutes for 80% capacity. CATL's Shengsing LFP battery, launched in 2024, supports 4C charging, full charge in 15 minutes, while maintaining a 400-mile range. Silicon anode batteries and advanced thermal management systems further enhance fast charging capabilities, addressing range anxiety and improving consumer adoption. 5. Battery recycling and sustainability. With EV adoption soaring, battery recycling is critical to reduce waste and recover valuable materials. Companies like Redwood Materials are developing closed-loop recycling systems, recovering up to 95% of lithium, cobalt, and nickel from used batteries. Additionally, sodium-ion batteries, which use abundant sodium instead of lithium, are emerging as a sustainable alternative for budget EVs, with KDL and BYD testing prototypes for urban vehicles. 6. Battery management systems, BMS. Advanced BMS leverage AI and machine learning to optimize battery performance, predict degradation, and enhance safety. These systems monitor cell health, balance charge distribution, and improve efficiency, extending battery life. For example, Tesla's BMS integrates with its software to provide real-time range estimates and optimize charging. Emerging wireless BMS solutions reduce wiring complexity, lowering production costs. 7. Structural batteries. Structural batteries integrate energy storage into the vehicle's chassis, reducing weight and increasing range. Tesla's 4,680 cells used in the Cybertruck are designed for structural integration, offering 35% more energy density than previous cells. This innovation maximizes space efficiency and improves vehicle rigidity, paving the way for lighter, longer-range EVs. The electric motor and battery are the beating heart of every EV, working in tandem to deliver efficient, sustainable performance. Electric motors, with their simple yet powerful design, convert electrical energy into motion through electromagnetic interactions, enhanced by regenerative braking and advanced power electronics. Innovations like axial flux motors, rare earth-free designs, and hairpin windings are pushing motor efficiency and performance to new heights. Meanwhile, battery advancements, solid-state technology, silicon anodes, LFP chemistries, and ultra-fast charging are addressing range, cost, and sustainability challenges, making EVs more accessible and practical. As of 2025, the EV industry is at a tipping point, with these technologies driving down costs and improving performance, bringing us closer to a future where electric mobility dominates. Whether you're an EV enthusiast or a curious newcomer, understanding these innovations highlights the incredible engineering behind the vehicles reshaping our roads. For more on EVs and cutting-edge automotive tech, like, comment, and subscribe to stay in the loop.